Okay, so we went through the discussion on the system engineering life cycle, and we discussed the phases and the stages for each one of the stages and each one of the phases of the system life cycle. So this second part of the semester, we're going to be looking at some of the details within each one of those stages, and we're going to start with the need analysis. So this is material that is covered in chapter 6 of your textbook, which is available online. And this is the agenda. So we've been talking about requirements. Obviously, is after you define your problem, stating the requirements is the next big part of it, of developing your system. So you want to make sure that you define those appropriately in a way that you can use them to build what the problem requires as a solution. So we're going to be talking about originating a new system, operations analysis, function analysis, the feasibility definition, the needs validation, and finally the system operational requirements. So the primary objective of the needs analysis phase of the system life cycle is to show clearly and convincingly that a valid operational need or potential market exists for a new system. Or it doesn't have to be a new system. You can also upgrade an existing system. So again, multiple examples, cell phones. We always get these upgrades. They have some new developments happening, new technology, so they can develop these new systems in a sense, but those are not coming from scratch. Those are coming from a major upgrade from a previous system. There is a feasible approach to fulfill the need at an affordable cost and within the acceptable level of risk. And this is one of the things that we discussed when we were defining the different type of requirements. We want to have a design that is not just functional, but a design that is buildable, right? That is implementable, something that you can build, that is feasible, that will fulfill the need at an affordable cost, and also satisfying a minimum or an acceptable level of risk. And we have talked about multiple examples in which risk and uncertainty have created problems. So that's why this is always connected to our design. We want to make sure that we provide the tests that are required. We want to make sure that we test for the different scenarios. So at the end, when we implement our system, it is something that can work and is achieving their purpose. So this is achieved in part by devising at least one conceptual system that can be shown to be functionally capable of fulfilling the perceived need. Describing it in sufficient detail to persuade decision makers that it is technically feasible and can be developed and produced at an acceptable cost. So most of the time you're going to start your sell for the new system with a proposal like you did for your project. You're trying to convince your customer or your boss or the person who's trying to fund this idea that this is something that you can create. There's technology, you have the knowledge to create this. And you can create this at the acceptable cost. And that could be any figure depending on the application that you're looking at. So in that way, you can persuade them to buy into your system. The place of the needs analysis phase in the system life cycle, as illustrated in this figure 6.1 from your book. You have seen this before. It is the inputs that are seen to be operational deficiencies or technological opportunities. So there's something that we can improve. It could be from the operational standpoint or from the technology standpoint. It outputs to the following phase, which is the concept exploration. There are the system operational effectiveness that specify what results a new system should achieve to meet the identified need. So how is this going to be better? what are the performance that this thing is going to achieve that is going to make it better? What are the system capabilities? What are the outputs of various operational analysis and system studies which provide evidence that an affordable, going back to the cost, system capable of meeting the effectiveness target is feasible. The cost is relevant. Okay, there's many ways that you can achieve the same goal, but affordable in the sense that not only will solve the problem, but it could be accessible to the people who are going to use it or to the people who needs the system. So there's some examples. I always bring the example of the car because it's the one that you're most familiar with. The car industry, government laws require manufacturers to make substantial improvement in fuel economy, safety, and pollution control. So every, I think, 10 years, these laws are revised and they are forcing the car industry to improve in their designs, make the cars more efficient, limit their pollution, and so on. Technology-driven new systems. These are applications of space technology to meet important public and military needs. Advanced devices such as powerful propulsion system, lightweight materials, and compact electronics made the engineering of reliable and affordable spacecraft a practical reality. Some other examples are these biotechnology products that are becoming very popular. So bioengineering, how can you use technology? How can you use technology inside the body to try to track some of the patient conditions, and how can you improve the functionality of some of the organs in the body, and so on. External events. This could be this is from the standpoint of originating a new system. External events often precipitate intensification and focusing on the process. In the defense area, that could be intelligence finding a new potential enemy threat, a local conflict that exposes the deficiency in a system. Like after Hurricane Harvey, there were a lot of things that were exposed in terms of deficiencies of the system. The system in general, like government agencies and so on. So that precipitated the need of new research, new development of new systems. So how can we align all these organizations? How can we align all these people that want to volunteer? So we want them to be placed in the way, in the area that they are needed, and we want to share the resources in a better way, more efficient way. So this is representing this type of event, the external events that can precipitate the need of new systems. In the civil products area, a triggering event might be a sudden shift in customer demand or a major technological change, such as the discovery of a new product or an opportunity to automate a labor-intensive process. So, for instance, I have seen some new applications of technology in conveyors. So conveyors that can by themselves decide where this box or item can go in your supply chain. So you don't need a person distributing or telling the box, or you go this place, this place. If you place some of these sensors, you can the conveyor can actually move. It is the same belt, but it has different change. So the change can change rotation to move the items to the different areas of the facility. So that's a change in technology that can save a lot of money in terms of labor, and you can use those resources in other places. So another example, the drastic increase in the price of petroleum has triggered an intensive and successful effort to develop more fuel-efficient commercial aircraft, like the wide-bodied jets. In terms of design materialization status, if we look at the needs analysis, the phases of the system development process can be considered as steps in which the system gradually materializes. We talked about this already in this phase, the needs analysis. This process of materialization has only just started, and that's shown here. So we are looking at things from the system perspective. We haven't gone into the details yet. We're still trying to figure out what is the need. We're trying to sell our idea. We want to make sure that we have a possible design that is feasible, affordable, and can be developed within a certain risk. Applying the systems engineering methods in the needs and requirement analysis, the needs analysis phase is different from most of the succeeding phases because there's nothing before that. There being no preceding phase. The inputs come from different sources, so your customer or maybe an exposed need, especially depending on whether the development is needs driven or technology driven. If you have a major development happening, that's an input. If there's a customer need, that's the need input for the needs analysis phase. Whether the office or the government or a commercial company. So that changes things. If you get funding from the government and if it is for research development, you don't necessarily have to have the limitations that our company will have in terms of data sharing or commercial rights. Government-related systems are made available to the public, so everybody can know about that. When you're looking at an industry project or a commercial project, those details are reserved for the company. You cannot share those activities and so on. The activities during the needs analysis phase can be useful discussed in terms of 4 basic steps of the systems engineering method with appropriate adaptations. Okay, so remember our discussion. We are talking about the system life cycle. Now we are going to apply the systems engineering method to that first stage of the system life cycle. So these activities are summarized below. First, the operations analysis. This is where we state the requirements. Typically include analyzing the project needs for a new system, either in terms of serious deficiencies of current systems or the potential of greatly superior performance at a lower cost by the application of new technology. Understanding the value of fulfilling projected needs by extrapolating over the useful life of a new system. Defining quantitative operational objectives and the concept exploration. So those are typical activities that will happen within this operational analysis. We analyze the projected needs. We understand the value of fulfilling the projected needs by basically looking into the timeline of how long this will be useful and defining quantitative operational objectives. The general products of this activity are a list of operational objectives and system capability. These are what the system is supposed to do. This is what we are expecting our design will do. And these are the operational objectives in terms of quantitative measures. Then from operational analysis or operations analysis, we transition to functional analysis. So we have an understanding of what needs to be doing, what the system should be doing after implementation. So how can we define functions that will satisfy those objectives or those goals? Typical activities include translating operational objectives into functions that must be performed and allocating functions to subsystems by defining functional interactions and organizing them in a modular configuration. So we have our the goal of the system. Okay, let's say we're talking about we need a new car that has to give me better efficiency. Now we want to establish what are the operational objectives. The car should weigh this much. The car should be giving me at least these many miles per gallon, and so on. Or it should be able to carry this many people. Now I have those objectives. How can I translate that into functions? Okay, so I needed this type of engine. I need this type of material, and so on. The general product of this activity is a list of functional requirements. Okay, so that's functional analysis, and then feasibility definition. This is the physical definitions. Typical activities include visualizing the physical nature of subsystems conceived to perform the needed system functions. Defining a feasible concept in terms of capability and estimated cost by varying trade-off the implementation approach as necessary. The general product of this activity, which is the third activity, is a list of physical requirements. The needs validation or the design validation. Typical activities include designing or adapting an effectiveness model, like an analytical or simulation, with operational scenarios including cost market factors. Defining a validation criteria. So, is this system is supposed to perform at this level? We're going to use a simulation model to verify that that can happen. Like if you are running a manufacturing line, for instance, and you've been running that manufacturing line for 5 years as part of your job, you have a very good understanding of the performance of that line. So if you are in charge of developing or bringing, like for instance, a new layout or a new machine, if you're trying to forecast the performance of that new line in terms of layout or in terms of using new equipment, you can build an analytical or simulation model with the performance of the new machine, for instance, and try to forecast and use that simulation model to model the scenarios that usually happen in your line and see how that new machine is going to perform under those scenarios. You have a benchmark already, which is what's been happening for the past 5 years, and you can use that benchmark to compare the new performance of this addition or changing in layout. If you see that the model is telling you that you are going to see a significant improvement, then you can move forward with that. But if not, then there's no purpose of implementing this new strategy. So we need to define a validation criteria. Validation criteria mean under these conditions, is it performing at least at this benchmark level? If not, then something's wrong. Demonstrating the cost effectiveness of the postulated system concept after suitable adjustment and iteration. So again, using the simulation model to see, okay, if I do this, this is the cost, these are the savings. Is this something that makes sense in terms of money? Am I saving something or am I improving some of my profit or not? Formulating the case for investing in the development of a new system to meet the projected need. Okay, so that's what I just mentioned. So is this system that I'm proposing, the investment for this, do I have a case for making this happen in terms of saving money or in terms of making my production more efficient? Given a successful outcome of the needs analysis process, it is necessary to translate the operational objectives into a formal and quantitative set of operational requirements. So this is this is what we just discussed as we've been doing lately in previous lectures. I kind of show you, this is coming from your textbook. a diagram that summarizes what we have been discussing up to this point. So if you see those arrows that shows the input outputs for each one of the areas of this systems engineering method: operational analysis, functional analysis, feasibility definition, and needs validation. And all this in relations to the needs analysis phase. Okay, so we talk about the needs analysis, we talk about the systems engineering method. Now we're going to focus on this part, operational analysis. Operation analysis, the first issue that must be addressed is the existence of a valid need or potential market for a new system, right? The development of a new system or major upgrade is likely to be very costly and will usually extend over several years. So if you, like, for instance, the development of the DVD, when there were VCRs moving to DVDs, you know that in order for you to recover the development of that technology, you have to wait these many years. So that's why you see the changes in technology in that sense not happening right away. Same if you go from VCR, DVD, and then Blu-ray, and now you have the 4K technology. So those changes are not happening right away. Even if we have the technology ready for the market and for the industry, those things needs to happen at different phases so they can recover these costly research investments. Same thing for medicines. So they put all these resources for research. They need to make sure that that investment is recovered before moving forward. Same thing for video games, video consoles, and so on. Accordingly, a decision to initiate such a development requires careful and deliberate study. The analysis of projected needs. Within the operational analysis, we can state what are the deficiencies in the current systems. In virtually all cases, the need addressed by a projected new system is already being fulfilled, at least in part, by an existing system. So unless it's a very radical technology, like something that you have not seen, typically that will happen in these major advances in space, research, and so on. But most of the time, new developments are based on previous or existing systems. One of the first steps in the needs analysis process is the detailed identification of the perceived deficiencies in the current system. So why is this current solution not good enough? Why? When I was building my house, at that point, the water heaters that were without tankless water heater were starting to be popular in the sense of being new technology. But when I was discussing with the builder, I was basically asking him what was the advantage of having a tankless water heater, because I have never heard anything bad about the water heaters that have a tank. I mean, there's no deficiency. They work properly. The only advantage that he was telling me was in terms of energy savings. That you will see a difference in terms of how much gas you are consuming. With the tankless, you don't consume as much. I think those are electric most of the time. But when you start looking at the research at that time, I don't know if that had changed, a lot of people were complaining that those were giving problems because the Clorox and the other things that comes within the water can get stuck in the system, and you need to repair them very frequently. So at the end, you have to think about, well, is this actually an improvement? If there's a deficiency, is this actually overcoming? Is the savings that you're getting for developing this new thing? And I have not seen many houses at least in these new developments that are happening in Austin. And again, I usually check whether or not they have the tankless because you can see it from the outside. And I don't see that becoming something very popular with new homeowners and new constructions. So same thing with the 4K. I mean, I know it's a new technology, but I don't see people adopting that technology. 3D movies, that was the other thing. It was popular at some point, but no, not a lot of people adopted the technology. So maybe, but it's important for us to identify this as a need. Is this something that is needed for the people? Is this something that people will use? Or is that need already fulfilled? So if there's no need, then we can keep the existing system. We don't necessarily have to develop something new just because we want to. We have to define that there's a need, that people will use it, people will buy it. So one of the first steps is in the analysis process is the detailed identification of the perceived deficiencies. You look at 4K and you look at Blu-ray, can you actually see the difference? Is that something that you will say, okay, yes, that change will make it buy or spend more money on a new system? The above process is most effective when it combines accumulated test data with analysis, often using existing system simulations. For customer-related systems, I guess surveys are also relevant. So if you have a system in which you're dealing with people, surveys can be a good way to see if they will adopt that new system that you're proposing. But if you're looking at system performance, technology performance, then system simulations will be the right way to go. This approach provides two major benefits: a consistent and accurate evaluation of the system operational performance and a documented history of results, which can be used to support the formal process of need analysis if a new development program becomes necessary. Obsolescence. The most prevalent single driving force for new systems is obsolescence of existing systems. So you can see that with cell phones. After the technology changed to touchscreens, you know that the previous technology was no longer used by people. So system obsolescence can occur for a number of reasons. For example, the operating environment may change. The current system may become too expensive. The parts necessary for repair might no longer be available. That's the case for some cars. That it's very hard to find parts, especially if they're coming from Europe or other places. When you still have a model that is old, it might get difficult to find the parts. Competition may offer such a much superior product. Technology may have advanced to the point where substantial improvements are available for the same or lower cost. So vigilant self-evaluation should be a standard procedure during the operational life of a system. Operational objectives in terms of analysis of projected needs. The principal outcome of operational studies is the definition of the objectives in operational terms that the new system must meet in order to justify its development. In a needs-driven development, these objectives must overcome such changes in the environment or deficiencies in the current system as have generated the pressure for an improved system. In a technology-driven development, the objective must embody a concept of operation that can be related to an important need. Although objectives should be quantifiable and objective, the reality is that most are qualitative and subjective at the early stage. Okay, so at the early stage, we're still trying to figure out some of the things that are going to be part of our system. So some rules of thumb can be helpful. Objectives should address the end state of the operational environment or scenario. It focuses on what the system will accomplish in the large sense. Objectives should address the purpose of the system and what constitutes the satisfaction of the need. Taken together, objectives answer the why question: why is the system needed? And most objectives start with the infinite word provide, but which is not mandatory. Okay, so I don't want you to get confused with objectives and requirements. Um, Basically, when you write these proposals, you for new systems, you start with a major goal. So the goal is your vision. A goal is not necessarily something that you are going to achieve with this proposal that you're stating, but your objectives come within the goal. And the goal, again, you might not achieve the goal, but the objective is something that is going to help you achieve that goal. So, for instance, if we are looking at renewable energy, our goal could be, okay, we want to have a cleaner or safer environment for a population of San Marcos. That could be the goal. But the objectives are, what are you going to do in order to achieve that goal in the long run? So are you going to be looking at limiting your consumption of gas, or are you going to limit your consumption of electricity and so on? In terms of objective analysis, the term objective analysis is the process of developing and refining a set of objectives for a system. Typically, the product of this effort is an objective tree, where a single or small set of top objectives are decomposed into a set of primary and secondary objectives. The composition is appropriate until an objective becomes verifiable, or you begin to define functions of the system. When that occurs, stop the objective. And this is an example or the idea that I'm trying to present. So we have the overarching objective, and then we want to use that objective to start defining our system and the things that the system must perform. So the idea here is that you start branching from this overarching objective. You start looking at how can you split this into pieces so you can achieve this major goal. And from those primary objectives, you can also split those until you start seeing that you can create some functions that will allow you to achieve that goal. At that point, you should stop. And I think I have an example that I'm going to show you. So for example, of an objective analysis, think about a new car. Suppose that the car wants to design a new passenger vehicle, like the one you're seeing here. This is the Tesla X model. Suppose which it can be marketed as green or environmentally friendly. So understanding the objectives of this new car establishes priorities for the eventual design. Thus, company management begins an objectives exercise. So forces the company to evaluate and decide what is important when developing this new system. Therefore, it is worth investing some time, energy, and capital in determining what the overall objectives of the system are. Moreover, agreeing to a concise single statement help focus the development team to the job at hand. So in this example, the company might soon realize that the overall objective of this new vehicle is to provide users with clean transportation. So the top level objective does not include performance, cargo capacity, off-road capacity, and so on. And the top objective or that clear or that clean transportation is the major goal. That's what you want to achieve at the top level. In the overall objectives are two keywords: clean and transportation. You want to be able to transport people in a clean way. Okay, so those are your two words. Both imply various aspects or attributes for this new car. Since both words are not yet well defined, we need to decompose them further. So this is but the overall goal is clear. This vehicle is going to be environmentally clean and will provide sufficient transportation. So we go back to this. I want to use that overarching objective and I want to start decomposing that. So here I start with provide clean transportation. So for me to be able to do this, I need to focus on clean and transportation. So clean in the sense of achieving a better performance, miles per gallon. And then in terms of transportation, it has to meet all the safety standards from the federal government, and it has to provide a comfortable ride for 4 passengers. And then finally, in terms of cost, it has to achieve a retail price of $15,000. So if you see in this diagram, these 3 objectives, you don't have to decompose them more, right? You have a way of measuring this, a way to measure this, if it's satisfying or not satisfying, and achieve a retail, you can also measure that. But providing a comfortable ride for 4 passengers, you can decompose that into more objectives. For instance, you can look at providing a sound system, allow normal conversation, and provide head, shoulder, and leg room for the passengers. So, and you can still go further in that area. So, how do you know when to stop? In determining whether an objective needs further decomposition, which one should ask a couple of questions. Does the objective stand on its own in terms of clarity and understanding? Can you verify the objective? Will decomposition lead to a better understanding? And finally, are requirements and functions really implied by the objective? If the answer is yes to all these questions, then you don't have to decompose them more. So in our example, we can argue that 3 of the primary objectives are sufficient as stated, and all the 3 are verifiable. Only one of them is subject to is subjective, related to the comfort needs and needs further decomposition. In this case, comfort can be divided into 3 components: sound system, noise level, and physical space. And what in the figure, these 3 could all be verified by various methods: satisfying survey in the first, a definition of noise levels for the normal compensations for the second, and volume requirements. Having an objective 3 focus on the development efforts on the priorities. So this is, I would say, one of the exercises that I would perform if I were looking at how to design my system. Like I know my overarching objective, I know the goal of my system, so I can start splitting these objectives and see until I can get into these functions, into these objectives that can be verified. Those are your requirements, basically. If you achieve that point in which you can verify your objectives, those are the requirements for your system. Questions so far? Questions? So from there we move to functional analysis. So at this initial phase of the system development process, functional analysis is an extension of the operational studies directed to establishing whether there is a feasible technical approach to a system that could meet the operational objectives. At this stage, the term feasible is synonymous with possible and implies making a case that there is a good likelihood that such system can be developed with the existing state of the art without having to prove in beyond reasonable doubt. So how do we translate these operational objectives into functions? Visualize the type of system that could carry out certain actions in response to its environment that will meet the projected operational objectives. This requires an analysis of the type of functional capabilities that the system will have to possess in order to perform the desired operational action. The visualization of a feasible system concept is inherently an abstract process that relies on reasoning on the basis of analogy. This means that all the elements of the concept should be functionally related to the elements of real systems. Okay, so as I mentioned, when you get to the objectives, you can start decomposing them until a point in which you can start defining functions. That's what we are trying to do in this point. So you have the way to measure, verify these objectives, and then you are going to start looking at ways of making those objectives happen. Those are the functions that the system must perform. In terms of feasibility definition, the feasibility of a system concept cannot be established solely on the basis of its functional design. The issue of feasibility must also address the physical implementation. In particular, system cost is always a dominant consideration, especially as it may compare to other alternatives. And this cannot be judged at the functional level. Accordingly, even at the initial phase of the system development, it is necessary to visualize the physical makeup of the system as it is intended to be produced. It is also necessary to visualize all the external constraints and interactions, including compatibility with other systems. Like in the case of electric cars, do we have the structure to support these new cars or this new technology? While it is necessary to consider the physical implementation of the projected system in the needs analysis phase, this does not imply that any design decisions are made at this time. In particular, no attempt should be made to seek optimal designs. That's something that's going to come later on. Those issues are dealt with most later in the development process. The focus at this point is to establish feasibility to meet a given set of operational objectives. It is the validation of these objectives that is the primary purpose of this analysis phase. So we have our objectives, we decompose those, we have functions associated to those, and these objectives are validated in terms of what this system must achieve. Visualization of subsystem implementation. Given the allocation of functions to subsystems, it is necessary to envision how this might be implemented. Okay, so we have all these functions. We can start grouping them. We talk about the modularity of the system design, the hierarchy of system design. So all those things are needed now. How can you establish a hierarchy for your system? How can you look at the modularity of these subsystems? So you can separate them as part of the overall design. It is only necessary to find examples of similar functional units in existing systems so that the feasibility of applying the same type of technology to new system may be assessed. So if you are developing a new transportation system that is going to be similar to Uber or to Lyft, then you can validate your new system based on that technology. Right? The same in terms of operational objectives. This is something that can be done because it's being replicated here or here. Relation to the current system. Where there exists a system that has been meeting the same general need for which the system is intended, there are usually a number of subsystems that may be candidates for incorporation in the modified form in the new system. And that's most of the time what you will see in technology. Computers, TVs, video consoles, video game consoles, and so on. So there's something already in place and you're trying to improve with the new system. Whether or not they will be utilized as such, they are useful in building a case for system feasibility and for estimating part of the development and production costs of the new system. Other less tangible factors can also come into play, such as the existence of a support infrastructure. and this is what I'm referring to with the electric cars. Do we have the support infrastructure to help in the use of this system? Relation to the current system, in the case of the car engine, many years of successful operation have established a very wide base of support for conventional reciprocating engines in terms of repair sites, part suppliers, and public familiarity. Because of the prospective cost for changing this base, innovative changes such as the Wonka rotary engine and design phase of the zero cycle has been resisted. The point here is that beneficial technology innovations are often overridden by economic or psychological resistance to change. So even though there are some alternatives to the typical engines, this can kill the development of new designs. Economic or psychological resistance to change. So here I'm showing this rotary engine, which is what I'm referring to here, and this is the starting cycle. Even though those are, I think this one is being used by Mazda in one of their models, they are not being used a lot. Application of advanced technology in technology-driven system is more difficult to establish feasibility by reference to existing applications. Instead, it may be necessary to build a case on the basis of theoretical or an experimental data available for such research and development works, as has been done on the candidate technology. In case this proves to be insufficient, limited prototyping may be required to demonstrate the basic feasibility of the application. Consultation with outside experts may be helpful in adding credibility to the feasibility investigations. So, how many of you have seen this show on Shark Tank? Have you seen Shark Tank? Yeah. So these are ideas. They don't come with the idea and they try to sell the idea. They come with an idea that has been tested already. So that's what we're trying to explain here. Sometimes just having the idea is not enough. You need to have a prototype and show that it is relevant, it is performing as expected. So you get the buy-in of your funding, for your funding. Cost. The assessment of cost is always an important concern in need analysis. This task is particularly complicated when there is a mix of all new and modified subsystems, components, and parts. Here again, cost models and maintenance records of the current system combined with inflation factors can be helpful. So for instance, economic analysis, your course in engineering economy is relevant at this point. You're going to use this inflation factors, you're going to use this net present worth analysis or annual base analysis to try to assess the cost for your system. By comparing similar components and development activities, cost estimation would at least have a credible base for which to work. In the case of new technology, cost estimate should contain provisions for substantial development and testing prior to commitment for its use. So this is something that was left out in that hover example. So substantial development and testing commitment in terms of having the money to perform those. And usually, if you're providing a bid for a project, I mean, an open, if there's a proposal that is open to many people and you have to provide a bid, this is where things get complicated. Because usually that decision is made in terms of, okay, this is giving me what I'm asking for at the lowest cost, and when you start cutting costs in order to gain or to win that bid, this is where usually you cut the money in terms of in order to win the bid, you might sacrifice some of these things, and that could be dangerous at the end, especially with these very highly cost projects. Definition of a feasible concept. To satisfy the objectives of needs analysis phase, the above considerations should culminate in the definition and description of a plausible system concept and a well-documented substantiation of its technical feasibility and affordability. The system description should include a discussion of the development process, anticipated risk, general development strategy, design approach, evaluation methods, production issues, and concept of operations. Needs validation. The final and most critical steps in the application of systems engineering method in the systematic examination of the validity of the results of the previous steps. In the case of the needs analysis phase, the validation steps consist of determining the basic soundness of the case that has been made regarding the existence of a need for a new system, and for the feasibility of meeting this need at an affordable cost and at an acceptable risk. And these are the statements that we begin with in this lecture. You need to make sure that you have a case for your system. In that case, the soundness in terms of making sense and that people interested in the system might buy in. It has to be feasible in terms of satisfying the cost and making sure that it's acceptable in terms of risk, or the risk that you're going to be facing. Operational effectiveness model. In the constant development stage, the analyses that are designed to estimate the degree to which a given system concept might be expected to meet a postulated set of operational requirements. All that is called operational effectiveness analysis. It is based on a mathematical model of the operational environment and of the candidate system concept being analyzed. In effectiveness analysis, the operational environment is modeled in terms of a set of scenarios. Postulated actions that represent a range of possible encounters to which the system must react. Set of scenarios. So if you are building a system that is going to be working at night, it's going to be working during the daylight, it's going to be working on cold weather, hot weather. Is that important for your system? You have to create these scenarios for testing purposes and see how the system is going to react. Usually, initially scenarios are selected to present the most likely situations, followed by more advanced cases for testing the limits of the operational requirements. Validation of feasibility and need. Finally, the effectiveness analysis described is mainly directed to determine whether or not a system concept defined or derived in the functional and physical definition process is feasible and satisfy the operational objectives required to meet a projected need. Okay, so finally we get into system operational requirements. So again, we are looking at the needs analysis phase. From the system life cycle, system engineering life cycle, and we are looking at the system engineering method, the steps of the system engineering method for this first stage of the system life cycle, the needs analysis, how to apply the system engineering method for that first stage. So we end up the discussion with the system operational requirements. The primary product of need analysis is a set of operational objectives, which are then translated into a set of operational requirements. The system operational requirements that result from the needs analysis phase will establish the reference against which the subsequent development of a system to meet the projected needs will be judged. These are the measurements that we are going to use to see if the system is meeting the need of the customer. These requirements are the things that we are going to look at when we are looking at the performance of our system and seeing whether or not it satisfies the customer needs. Operational scenarios, we talk about this. These are all the areas that, or all the environments, or all the scenarios in which your system is going to perform. The logical method for developing operational requirements is to postulate a range of scenarios that together are representative of the full gamut of expected operational situations. So these are all the things that the system is going to be facing. Do we need to specify requirements for each one of these scenarios? Well, scenarios range widely in their content depending on the application. We are able to define 5 basic components of almost all scenarios. 1. The mission objectives. The scenario should identify the overall objectives of the mission represented and the purpose and role of the system in focusing and accomplishing those objectives. In some cases, this component is system independent, meaning that the role of any system is not presented, only at the general description of the mission at stake and the objectives sold. For example, in a commercial example, the mission could be to capture the market share. In a government example, the mission might be to provide a set of services to constituents. In a military example, the mission might be to take control of a particular physical installation. So depending on the application, depending on the scenario, the mission will be different. Architecture, the scenario should identify the basic system architecture involved. So if you're going to be using a system that is going to stay outside, then you have to provide a way to keep the system safe. You have to provide a way of keep the system or make the system resist all the weather conditions and so on. So that would change your system architecture. This includes systems, organizations, and basic structural information. If governance information is available, this will be included. The component could also include basic information on the system interfaces or a description of the information technology infrastructure. In essence, a description of the resource available is provided. In a commercial scenario, the resources of the organization are described. In a government scenario, the organizations and agencies involved in the mission are described. In a military scenario, these resources could include the unit involved with their equipment. Physical environment scenario should identify the environment in which the scenario takes place. They will include physical environment, terrain, weather, transportation, grid. This is what I was referring to in the previous one, as well as the visitor environment. Neutral entities are described in this section. For example, customers and their attributes will be defined, or neutral nations and their resources. Competition, the scenario should identify competition to your efforts. These might be elements that are directly opposed to your mission success, such as software hacker or other type of enemy. This may be your competition in the market of outside forces that influence your customers. This could also include natural disasters such as tsunami or a hurricane. So how this can affect your system, that's part of your competition. And finally, general sequence of events. The scenario should describe a general sequence of events within mission concepts. The scenario should allow for freedom of action of the players. Scenarios typically provide a general sequence of events. The details to analysis using the scenario. At times, a scenario may provide detailed sequence of event leading up to a point in time, whereby the analysis starts and action might be authored from that time forward. When I was a PhD student, I was involved in a project for developing a decision-making system for containing fire that spread on the forest. So we needed to generate this type of analysis scenario that will tell you, okay, if we start at this point, of the fire, how your system will react. If the fire is starting, if the fire is at this point, if the fire has already spread this much. So you have to provide those sequence of events because you need to know, I mean, you don't know at what point you're going to be called, or what point you're going to be using your system. So a scenario can include much more depending on its application and intended purpose. They come in all sizes, from a short graphic description of a few pictures to hundreds of pages of text and data. The only means for judging whether or not requirements are complete is to be sure that all these situations are considered. For example, the range of temperature or humidity of the storage site may drastically affect the system life. And that's the end of this lecture on need analysis. So